Thank you very much, and good morning, everyone. And thank you all for being here listening. I would like to, I'm from the research group Electrochemical and Surface Engineering of the Free University of Brussels. And I would like to tell you a little bit, this is a slightly different topic than the two talks before, about how we use scanning Kelvin probe force microscopy for research that is relevant in the field of electrochemistry. Maybe how can I put the spotlight? Is it this one? No. Well, so briefly to briefly to remind you, even though many of you are probably familiar with the concept, scanning Kelvin probe force microscopy is basically based on the scanning Kelvin probe principle. Two electrodes brought in contact with each other, which are also in an electrical contact. At the close contact between the two electrodes, we are able with this technique to calculate the contact potential difference between the two. And this contact potential difference is actually very much related to the differences in the work function between the two electrodes, in which one could act as a sample, the other one as the probing element. Now, this work function, it's a concept that it's not a bulk property of the material. It's very much sensitive to the surface. It's a surface property, and it's very much related to concepts like the volta potential or the Fermi level. Therefore, their use on the field of electrochemistry, which is not actually a new thing. And absolute values of the work function are actually possible, but you need a kind of calibration. You need to know the work function of your tip. However, in most studies using scanning Kelvin probe force microscopy, this is not done, and we just use, if you assume that the work function of your tip of the probe, it's constant along the full scan, then the differences in scanning positions, the differences in this contact potential difference are going to be differences actually in the work function between the different spots. Now, we are an electrochemistry group. We have an AFM, and we do several studies involving the use of scanning Kelvin probe force microscopy for this field, in the field of electrochemistry. And I would like to tell you briefly in 3 case studies the way we use this technique. The first one is on the use of scanning Kelvin probe force microscopy to understand the pitting corrosion initiation. In this field, this is not new also. It's been studied for over 20 years, the use of KPFM for understanding corrosion initiation. And the principle is very simple, it's very standardized. Many groups use this concept, basically due to the presence on alloys of intermetallic particles or intermetallic precipitates. These alloys are vulnerable to corrosion, pitting initiation, because of these differences in phase that are formed then within the material. Now, what you do with the KPFM, you do a potential mapping of your surface, and you see surfaces, phases that have a higher potential in contact with phases that have a lower potential are vulnerable spots for pitting corrosion initiation. How it happens is, if a phase has a low work function, a low electrochemical potential, then it will be acting like an anode in the presence of a corrosive media. And this explains the possible underlying mechanism of the corrosion initiation. This is an example of an alloy in which intermetallic precipitates have a higher potential than the matrix, However, you can also find the other case in which the one below, in which intermetallic particles could have a lower potential than the metal matrix, and explain the corrosion mechanism after exposing them to a corrosive environment. What do you see in the first case? These intermetallics are exposed, and the matrix around them it's dissolved. Because it has a lower potential, it acts like a kind of a galvanic coupling effect. They are in close contact, they are in contact, electric contact with each other. Therefore, the matrix here will dissolve preferentially, exposing the precipitates. However, in the other case, the metal matrix remains intact, and the inclusions, these inclusions are the ones that preferentially dissolve in a corrosive environment. And this is explained by using this scanning Kelvin probe force microscopy. It gives some very interesting insights on the initiation of the pitting, the underlying mechanism of this pitting corrosion initiation. However, this technique, which is now very much standardized, has also been kind of misused. And this is a work that we have recently done. This is an example of another alloy. It's an iron alloy, it's steel with these inclusions in it. After immersing it in a corrosive media, you get the dissolution of the metal matrix around the inclusions. If you would do a potential mapping on these inclusions, you will find out that actually these inclusions have a higher potential than the steel matrix, therefore explaining these mechanisms to be the result of a galvanic coupling effect. However, this is actually not the case, because these inclusions are actually insulators. There couldn't be any galvanic coupling between them and the matrix. So this use of KPFM for corrosion studies, even though it's very simple, it's very standardized, should also be taken with care. Not everything can be explained by using this technique, even though it looks very simple. The second case study I would like to show you is about how we use scanning Kelvin probe force microscopy to monitor the repassivation of aluminum in air or other metals. We validated this technique on aluminum. And basically, most metals and alloys in air, they are covered by a native, naturally grown oxide layer, which is a very thin layer of a couple of nanometers thick. But it's a very important layer that it plays a very important role in the interaction of the metal with the different environments. It plays a very important role on corrosion. It plays a very important role also on the thermal stability, on the friction of the material. Now, the growth of this oxide layer it's actually due to the presence of oxygen in air or even immersed in liquid environments. If this oxide layer is damaged by scratch, for example, there is usually a very fast repassivation. Depending on the material, it's how fast it is. Now, this growth kinetic of this native oxide layer, it's very important also to understand the mechanisms of stress corrosion cracking, corrosion fatigue. Basically, the faster the repassivation, the better the corrosion resistance of the material will be. This layer acts like as a barrier for certain metals for corrosion to occur. It kind of passivates the metal in the presence of a certain corrosive media. Now, this is the methodology that we have developed by using scanning Kelvin probe force microscopy. We basically scratch the surface, like the one shown here, and we do a scan, like this rectangular area that I'm showing here. Important is that this scan takes an area within the scratch and an area within at the untouched part. And we do a topography and potential mapping of this area. Topography is mainly used to really evaluate and make sure that you are in the right spot. The potential of this signal is what we will use. And this is an example of a line scan of this potential. You see, even though there are great irregularities within the scratch, the potential is quite stable. And there are two main characteristic values of the potential, one within the scratch and one outside of in the unscratched zone. You can see this easier maybe if we build a histogram of all the potential values here, and you do see the two main contributions to the potential. Now, the only difference between inside the scratch and outside is actually the absence of this native oxide layer. And therefore, the value within the scratch has a lower potential. There is a lower work function. There is a lower chemical potential because the metal is actually exposed there. Now, if we monitor this with time, we do several scans. We don't have to do a full square scanning. A rectangular scanning is actually easier because then we save time. We can do resolve this better in time. And we do several scans with time. Here is a topography. This is on the left. This is a different scratch. Now the scratch is on the left. You see the great irregularities within the scratch and the topography. When you see the potential evolution with time, this is only some examples of selected times and selected line scans. You see then the part that has not been touched has a very stable value of potential. However, within the scratch, the potential tends to increase with time. And this is exactly due to this repassivation of the native oxide layer, which actually in aluminum there have been already a lot of studies relating the value of the potential measured with KPFM, and there is a linear relation almost with the thickness of this native oxide layer, which is then very interesting in this case. If we take the value here at the unscratched zone as a reference, we can then take the difference between within the scratch and the other area and build a potential difference which will actually reflect the kinetics of this repassivation of the native oxide layer. We then did several fittings of the data, and we found out that the results fit very well with proposed theoretical model for the kinetics of this, the growth of the native oxide layers on aluminum. We have used already these studies for studying, for example, the influence of alloying elements or the influence of microstructure on the kinetics of this native oxide layer with very interesting results. Now the third case study that I would like to share with you is how we've been using scanning Kelvin probe force microscopy to study battery materials, to study lithium-based cathode materials. And this is some work that I have done in collaboration with my colleague Xinhua Chu. This is an example of a commercial, taken from a commercial battery of this electrode. This is a cross section that shows that actually it's a rather thin electrode. This is very important because it assures that there is no normal distribution, normal gradient of this charge, or at least the effect of normal gradients, it's not so high. It's very simple, the methodology we developed. We basically charge our battery material to different states of charge, to different potentials, and we scan several points of the surface. We do scanning Kelvin probe force microscopy mappings, and the potential maps of this that we obtain, we average the values of all the potential maps and correlate each potential value that we calculate with a specific state of charge. The fact there is a higher than 100% here is just a matter that we take this as a value, as a cutoff potential. Wherever is higher, that's an overcharged state. but it's all relative. We choose what potential will be the potential at which we charge at 100% state of charge. And then when we correlated all of this with the charging curve and the potentials that we measure for each state of charge, we actually found a very nice correlation between the two, between the electrochemical potential and the potential, the contact potential difference measured with the scanning Kelvin probe force microscopy. This is actually very logical. This is very much related with Fermi levels of the material, with the work function, with the chemical potential. Therefore, it is only normal that we get this linear relation. Then it's like we could use this as a calibration curve. This linear relation between both a potential measured, the potentials measured with the Kelvin probe force microscopy and the electrochemical potential of our battery material. This is like a calibration curve, and we can then go back and for each potential map actually associate this value of potential obtained with a specific state of charge. And for example, in this battery, the material that was charged to a certain potential, we do the potential mapping. We can even see inhomogeneities, study inhomogeneities within the material. And actually these examples of A and B, these two particles, are very close to each other. However, they have very distinct values of potential, which can be translated to specific state of charge. Or what is the same, we can actually do directly from the potential a state of charge mapping of your electrode. An example of a cluster of two relatively large particles, and how you see that even though they are very closely connected to each other, they have difference in state of charge. And these studies have been actually very important for us. They have given us very interesting insights on the aging, the effect of inhomogeneities on the degradation of these materials, how inhomogeneities actually affect the faster degradation of the material and how it works. We are able to map with these overcharged states and how a possible growth of this overcharge could happen by continuous cycling of the material or high temperature cycling. So this is a very interesting methodology which we are actually further exploring, and even in other electrode materials. I think I am on time. I would like to thank you all for your attention, and thank all my colleagues also, especially those involved with me that collaborated in these works, like Xinhua Chu is hiding here in the right corner, and Chao, which is his note in the pictures. Thank you all for your attention.
All right, thank you, Reynier, so much for your talk. So let's have a look at the question. We have one nice question coming from Daniel Steinbach. And Daniel is asking you, how did you achieve the scratch on the surface? Is it reproducible?
Yes, actually, this is the ideal case. What we wanted is actually scratch with the actual tip, but then the scratch will be very small. The scratch is done outside with a steel scrap. We scratch the surface and quickly start the time start counting. So we lose actually maybe 3 to 4 minutes, and we place immediately the sample in the FM and start measuring. So it's all about being fast, finding quickly the spot, the scratch you did, and scanning. Interesting is I've done several measurements on this, many places on the scratch, and it's actually very reproducible. I show in the paper that is listed there many measurements done that actually the reproducibility is very good.